The show on the road here. I'll start with questions from 4.1, and then we'll do a little 3.9 stuff and then move forward into 4.2. So if you guys have questions from 4.1 homeworks. Do I need to make required homeworks to get you to do stuff in between? I understand. I understand that you're real busy. I get it. But can we try to make a little bit of time for this? Even if it's just I did 3 questions. That's better than nothing.
I was able to finish it.
Good.
I did.
Good. I'm glad to hear that. I just want to I know I said we were going to stop doing the homework quizzes because this is going to be an open homework test. But really, guys, it is. Hi, Bladen.
I know.
Good. What's up?
I left my calculator.
Oh yeah, right there.
I think it was charging for 2 days.
You know what? It should be good to go now.
Yeah, there we go.
It's as charged as it's gonna get, anyways.
Yeah.
Have
a good class.
Thanks. But it is, especially for a course like this where you're doing things that you've kind of never done before. And this is a chapter where really the ideas build on each other. It's really gonna be massively to your benefit here to make sure that you're doing some of the assignments in between classes. Okay? I don't want to harp on you guys. I know you're busy. I know feel like you're pulled in all the directions in the world. I know you have a lot of other hard classes. And I'm not talking about you need to do everything. But pick a couple and do something, right? Even if it's just a handful. That's great. I mean, I can live with a handful in between. Ideally, you do all of them, but let's be realistic. That's probably not realistic for everyone. But do a handful, okay? Just try to make it a priority. Make some time. Not talking about all the time in the world. Elena, did you have a hand for questions? Yeah, let's start with you.
27.
27. Great. So our directions for 15 to 27 says to sketch the graph by hand and then find the absolute and local max and minimas for F. Which one did you say, 27?
Yeah.
Okay. Where's my writing thing? What's that thing called that you write with? That's the name of it. I have too much junk. So let's talk about how to graph this. It's a piecewise function, right? So to graph this by hand, I'm going to make an XY table for each of my pieces for my piecewise function. Now, each of these pieces, what type of function is y equals 1 minus x? Linear. So how many points do I need to graph that? 2. What 2 values of x do I need to include? 0 and 2. Why 0 and 2? Yeah, that's the interval over which that function is defined, right? Great. Same thing for 2x minus 4, correct? So that would be the point 1 or 0, 1 and the point 2, negative 1. And then I'm going to put a star here next to 2, negative 1. Why do you think I'm making a special note next to that point? I'm just plugging Yeah, because it's an open circle when I graph it, right?
Yeah.
I just plug the x's in, Elena. I'm going to do the same thing over here, so I get 0 and 2. So if I plot this thing, so 1, 2, 3. So I have 0, 1, 2, negative 1, and then I have 2, 0, and then 3, 2. So there is my graph. Let's start with the absolutes. Because it was a strict less than. Everybody's so far so good? Okay, absolute max. Yeah, the 0.32 is the location of our absolute maximum, right? Let's read the question here real quick. Want the absolute and local maximum minimum values of f. So what does it want there? The y coordinate. So maybe I'll write this then as like f of 3 equals 2. Be a little bit clearer there. Probably just list 2 if this is a multiple choice question. So don't be confused. If it wants the maximum value, it's talking about a y coordinate. All right, absolute minimum. It's not 0. It's not -1. It's not 1.
What? Is it non-existent?
Ah, there you go, Talik. It's not existent. Why doesn't it exist?
Because like open circles.
Because that open circle, I can get infinitely close to -1, but I can't get there. So if you give me -0.9, well, I can say, oh, -0.99 should be in there. That's closer. And you say, okay, well, take that one now. And be like, well, what about -0.999? Well, that's more negative, but it's, and I can do this forever, right? So there's no absolute maximum, absolute minimum. Everybody's cool with the explanation there?
Yeah.
Okay. How about local maximum? What would that be? What? Doesn't exist is correct again. Remember, the local mins and maxes have to be in an open interval, right? So if you say like, oh, this looks like it maybe is a local, right? Okay, so the open interval that I would have to include something to the left of that jump, and then I'm in the same position as before, right? Because I can't do a closed interval including just 0 and have 0 be the location. You know what I'm saying? So because I have to pick an open interval surrounding that, what I think is my minimum, means I need some points on the other side of that jump discontinuity, and that means I have to include the open circle, whether I run into the same problem as I had for the absolute minimum.
So it just can't be an endpoint.
So you can't use an endpoint, 100%. Oh, that was, I said minimum there. Almost put that in the rocks. How about local maximums?
Non-person does not exist.
Sure. Yeah, I think that's fine. How about the local maximum? Good, agreed. Does that match what the back of the book said, Elena? Okay. I assume since you asked about it, you checked it, and were like, how did you get this? And no, it's okay. No, it's all right. I just pick in. I'm going to talk to Isabel for a second while you're looking that up for us. Sound good?
Yes.
So for like
Perfect.
the endpoint situation, I thought that only applied to like absolute like maximum.
Absolute maxes and mins can be endpoints. Because if I go back and I look at our definition that we had for an absolute max or a min, it says for all x in the domain. So if our domain is closed interval, then the endpoints can count. The local is x near C. When we say near, we mean an open interval. In that case, endpoints cannot count. Does that feel good?
Yeah. Thank you.
Here, I guess when we say endpoints can't count for a local, I guess I should be careful there because that's not expressly true. Okay, can I give you a little small counterexample? I can change this same problem so that there is a local minimum. If we do that, if I make this one the filled circle and that the open, because then if you do something like that, an open interval surrounding this, that is the lowest point in there, right? It's fine. So if we did that, and then we pick an open interval, that open interval can include the minimum. Now that'll also be an absolute minimum, right? But there's a case where an endpoint can be a local. Does that feel okay? So again, you have to really be careful, right? You have to think about like, okay, can I draw an open interval that includes this as a lowest point? And if you can do that, then it can, that point can still be our minimum, our local minimum. Tess, does that feel okay? So now if I draw an open interval, this point is included, right? That's our minimum. So it's fine, even though it's an endpoint of a segment. The problem before was that the lowest spot was not where the minimum is, right? The fact that the minimum is still closed is what saves us there. And just think about it this way maybe for a moment. If we allowed this thing to be a local minimum, then it would also have to be an absolute minimum, and it can't be that, right? Like something can't be local and be the only local minimum on a closed interval and not be like, oh, I guess maybe I shouldn't say that. That's a lie. Nope, I don't want to say that. Never mind. I just drew the counterexample in my head. I'm not finishing. I was wrong. Who's next on questions? Beck. 57. Getting deep in here, huh? But that section of questions that Elena just asked about are good ones because they are really like building some intuition, right? We're just kind of drawing a picture, looking at the result. If you really got stuck, anything that's not piecewise, what could you do with it? Graph it on your calculator, right? Most of these things we should have some kind of a little bit of intuition about how to graph. At this point in our mathematics careers, I would hope you could look at most of these things and be like, okay, I know what the shape is going to look.
Do you think a question like that would be on the multiple choice?
Probably they would give you the picture to go with it.
They won't really be having to graph that on multiple choice.
I would not think so, unless it's a calculator-based question, which they expect you to just kind of like type into the calculator and see what happens.
Multiple choice.
There's a multiple choice section that has calculator and a multiple choice section without calculator. That's why the last test we did multiple choice with the calculator instead of.
So you do get it for that.
There's two sections of each. A FRQ with calculator and FRQ without. Multiple choice with calculator, multiple choice without. And so I'm trying to make sure that we've been practicing calculator, no calculator kind of throughout.
In my mind, originally just did a calculator all the way.
Oh, no, as we get deeper in, there'll be some stuff that we'll ask you to do that like you just can't do by hand. They just wouldn't expect you to be able to do by hand. And realistically, like I wouldn't know how to do it by hand.
Okay. That's really reassuring.
But you can easily do it on the calculator.
Okay.
And in fact, on that last On the last test, there was the question about like finding the k, the value for k on the, it was an ellipse or something was what the shape of the thing would have been if you could have typed. It was implicit. And the only way to find that k, you couldn't have done it algebraically by hand. Like I can't do it by hand. Nobody would be able to do it by hand unless you're using some kind of like approximation method, or you graphed on the calculator and like looked for an intersection or looked for a zero or something. So that's not uncommon. Okay. So 57, the directions say find the absolute maximum and absolute minimum values of f on the given interval. So first thing we should check is what the domain of f is. If we look at that, what is the domain of 2 cosine t plus sine 2t? All real numbers. Great. How did you know that? Sine and cosine's domains are both all real numbers, so the sum of them has to still be all real number, right? Everybody's good? But that's not really what we're working with. If the domain is all real numbers and we're just concerned about 0 to pi over 2, then clearly its domain is still 0 to pi over 2, right? So far, so good? Okay. Let's do the derivative then. So derivative of 2 cosine t. Negative 2 sine t. Good. And the derivative of sine 2t. 2 cosine 2t, right? Everybody's good? Okay. What's the domain for this? Again, all real numbers. Very good. How do you know that? Yep, you're just sine and cosines again. Instead of writing all real numbers this time and crossing it off, I'm just going to write the domain. So we don't have any critical numbers that are due to the function or the derivative being undefined, right? The only critical numbers we're going to have are going to be a result of setting this equal to 0. How are we going to do that? Sure, we can divide a 2 out. Sure, that's true. Why not, right? Yes, if you're going to do this by hand, you would be relying on a trig identity. It's a double angle identity for cosine. So I remember the simple one is, I think it's cosine squared minus sine squared. I don't remember. There's 3 versions of it. Yeah, see, there's 3 versions of it. I remember this version, then I would have had to derive this next one, but 1 minus 2 sine squared. I'm going to just write it down as if I remembered it. Okay? Now, if you had calculator active, what else could you do? Yeah, I could just graph this on the calculator, right? Everybody feel okay? Oh, thank you, sine squared. Thank you. Yep. I'm going to go and divide a negative sign or negative through so that looks like this. Now, how do I solve something like 2 sine squared t plus sine t minus 1? You could factor this, or what else could we do? Yep, looks like a quadratic. That's exactly right. Or you could apply the quadratic formula, but instead of solving for x, you'd be solving for sine t equals negative b plus or minus square root b squared minus 4ac all over 2a. You could do that. This factors So let's just do that. So which one should be the plus and which one should be the minus? Where the plus goes in the first one or the second one? The second one, because I need positive 2t, or positive 2 sine t, and then minus 1 sine t to get to the plus 1 sine t in the middle, right? So I solve these, or set these equal to 0 using the zero product property and solve. So where is sine equal to 1/2? Pi over 3 is not correct, and pi over 4 is not correct.
I believe that pi over 6.
Pi over 6. And
And 5.
yes, very good. Nice showing off.
Thanks, guys.
And then where is sine t equal to -1? Nope. Nope. 3 pi over 2. Y, sine is y. So on the unit circle, it's where the y coordinate is -1. Yep. But what is the domain here for our inverse, or our derivative? Excuse me. 0 to pi over 2. So those guys don't count, right? Okay. So we have just that. Now, to check whether that's a maximum or minimum, or define the maximums and minimums, I'm going to do f of 0, f of pi over 6, and then f of pi over 2. And the biggest value is going to be my maximum, the smallest value will be my minimum, and the other value is, I don't know what it is, but I don't care what it is. Everybody cool? All right, so if I plug 0 in, what was my thing again? 2 cosine of 0 plus sine of 2 times 0. What's that? That's 2, right? Okay. What is cosine of pi over 6? Root 3 over 2, very good. Again, that should be easy to remember because we knew that sine of pi over 6 was 1/2. And those two are always the coordinate pairs, right? And then 2 times pi over 6 is pi over 3. What's sine of pi over 3? Should be easy because we know sine of pi over 6 is 1/2. Also root 3 over 2. Because we know that complementary angles, they're just like, the coordinates flip or whatever, right? So that is root 3 over 2 times, or 2 plus 1. There we go. Or 3 root 3 over 2. Is that bigger than 2 or less than 2? Bigger than 2, I would think, right? Because it's like 1.5 times 1.6. Square root of 3 is like 1.69 or something like that. I'm just kind of approximating. So this is now our new candidate for a maximum. And then our last one, 2 cosine of pi over 2 plus sine of 2 times pi over 2 equals. Cosine of pi over 2 is 0. Sine of, well, 2 times pi over 2 is pi. Sine of pi is 0. So that looks like our max and our min. Braden?
How do you know that the maximum is just the two and the meter?
Okay. So I know that if my function is continuous, any place where I have a max or minimum, the derivative is going to be 0, or the derivative could fail to exist if I had something like this. So those are the only place I need to check. Those are the only possibilities. It's either at an endpoint, which could be higher or lower than wherever I have a minimum, like an extrema, or the extremas. That's it. That's all it can be. And it's because it's continuous. If I lose continuity, all bets are off. Like crazy things could happen. Yeah. Yep. Pierce.
So in this problem, after you took the derivative, the domain still stayed as all real numbers. You're ever gonna have something where it'll change.
Absolutely, you can.
So what would you do?
Well, anything that you lose in the domain
Yeah.
becomes a critical value.
Okay.
So that's just something else that goes into the pool of values to test with f.
Okay. But you would still use
I still use my endpoints,
Okay.
and I still use all the critical values, whether it's where the derivative fails to exist or where the derivative is 0. All right. Let's go ahead and do another example from 3.9. Let's do a 3.9 one. I'm going to choose one from the multiple choice. Oh, sure. What's up?
It's gonna sound stupid.
No, it's okay.
Can we just differentiate this part of 33?
Sure.
I don't know why it's
Messing with you?
a little bit.
Yeah, sure thing. This is f of x equals, is it x squared e to the negative 3x? Okay. So to do the derivative, that's going to be a product rule. So we just set it up this way. Feel good? To do the derivative of e to the negative 3x is a chain rule. So the derivative of the outside is just e to the 3x, or negative 3x, excuse me. And the derivative of the inside is the derivative of negative 3x. And then derivative of x squared is just 2x. Here. And now, for sure, some of us are at the point where we're doing stuff like this in our head, and that's okay. And if you're not, that's okay. But I want to write out all the steps here, apply a rule and write what the derivative is that I'm taking for the next step, and just be real clear about what happened. So what I'll do now is, the calculus is done. If I wanted to put this in a form in which I'd be trying to solve from here, I would factor out the e to the negative 3x. And what I'd be left with is 3x squared plus 2x. And then you can apply the zero product property and kind of solve from there, which I assume is not a big deal, right? Good. Okay. All right. So 3.9, I wanted to look at, I think the worst one in here that's not the free response was 14. Rita's like, I didn't like that one. And I think this is a nice one because the formulas that we're using are stuff that you should feel or should have at your disposal that you should feel pretty good about. But the algebra gets a little yucky on how to eliminate your variable. I just want to grab my work I did on this so I make sure I don't do extra stuff that I don't need to. All right, so this says a model car travels around a circular track with a radius of 5 feet. Let Z denote the distance between the model car and a fixed point that is 20 feet to the left of the center of the circular track. That's O in this case, if you couldn't tell from the picture. The diagram indicates the fixed point at the origin, the center of the circular track at the point 20, 0, and the position of the car at the point x, y. Z is the length of the segment from the origin to the point x, y. If x and y are functions of time, t, in seconds, what is the rate of change of z when x is 23, y is 4, and dx dt is 2? And then they give us a hint that tells us the equation of a circle with radius r and center h, k is x minus h quantity squared plus y minus k quantity squared equals r squared. So let's write down what we know. So we're looking for dz dt when x is equal to 23 and y is equal to 4. So far, so good. What is z representing again? Yeah, the distance from the origin to that point x, y. What equation can we use to write that? The distance formula. Yeah, do you remember the distance formula from geometry or even algebra 1?
Square root of x squared plus y.
Everybody's okay here? Let's make x2, y2 the origin. So this just becomes, and let's make xy our x1, y1. And instead of calling this d, I'm going to call it z. Everybody feel okay there? Now, the problem is if I differentiate this, I'm going to end up with a dx dt and a dy dt. Do I know anything about dy dt?
No.
I do not. So I'm going to have to find a way to get rid of that y squared in this formula. Everybody, so far so good? What piece of information that have they provided that we haven't used yet? That equation for a circle. So let's write our equation for a circle. So we have x minus, what's our h in this case? 20, good. And then we have y minus k, what's our k? 0, okay. And equals r squared, and what's our r? 5, right? Told us in the problem the radius of the track was 5 somethings feet. Okay. So if I look at this, if I simplify things down here a little bit, but not too much, I notice, hey, that's an equation with a y squared in it, right? Let me just get that y squared by itself. And now I'm going to substitute this in for my y squared. Pretty slick. Yeah, that's not bad, right? Okay. I can get on board with this. Now, depending on what your tolerance is for algebra versus calculus, you could FOIL the x minus 20 squared out and do some combining of like terms before you differentiate. Or you can differentiate as is. I don't think it makes it much more difficult. I wouldn't bother to FOIL this out to differentiate, but just depending on taste. But now we have something with just x's. So let's do the derivative. To differentiate the square root of x squared plus 25 minus x minus 20 quantity squared, I need to use chain rule. Great. What's the derivative of the outside going to be? Yeah, 1/2 times the insides to the negative 1/2, and then times the derivative of the insides, right? What's the derivative of x squared? What's the derivative of 25? What's the derivative of quantity x squared or x minus 20 squared? Good. Everybody feel okay doing that? Okay. That's dz dt for us. So what do I need to do here? I just plug in 23 for x. Did I need the y equals 4? No, man. So now it's just like calculator time, right? Is it okay that I just wrote that as 3 instead of 23 minus 20?
Why did they give us what dx?
Oh, shoot. Yeah. Good. Thank you, Jacob. What did we forget?
What is dx?
Yeah. Just 2 places. Thank you. What was dx dt again? 2. Thank you. I absolutely am recording. And then it's just type in your calculator time, right? I think you come out, if you cared to hang on to it and do all the algebra, I think I get 40 over 545, or root 545, I should say. Which I think is what our answer was for B. Notice it gives you the decimal also, right? Because I think this was designed to be a calculator active problem where they expected you to use your calculator if you needed to. I don't think you needed to, but Brayden.
Why do you want to see away or towards?
So since the derivative is positive, that means the length of d should be, or the length of z should be increasing, so that car should be moving away from the origin, because it has to be, the length of z should be getting bigger, right? If it was a negative, then it would be moving towards the origin, so the length of z would be getting shorter. Does that feel okay? Jacob. Oh. Away and towards.
Oh, I didn't do that.
Yep. That is the same number, though. Pierce.
So with your fraction that you got as your answer, like since you have a calculator, would they expect you to convert it to a fraction or a decimal?
They gave you both in this problem.
Oh, okay.
Notice they gave you both. So I think it didn't matter. Yeah. I mean, I would have, seeing this and knowing it's in the calculator section, I would expect decimals to be in my multiple choice answers as opposed to like a fixed radical like that. But I mean, take a moment, look at what your choices look like and be like, okay, can't just type this in my calculator because I have to have a radical in this at the end. Although I guess you could just take this and type in your calculator and see if it matched the decimal that you got. That'd be okay too. Emma. Of course. Rita.
How do you know that's over? Not
Because the derivative is positive, that means that the value of z is increasing. So z was the distance, and the only way that distance is getting longer is if the car is moving away from the origin, since that's fixed. Is that
yeah, that makes sense.
okay?
And also, could you see or 15C?
15. Oh, I didn't necessarily want to get into one of these today, but we can do that. I just am worried about running out of time. Yeah, we're going to continue to do like 3-9 stuff all week, which I feel like is probably in everybody's best interest to just like see it a little bit at a time rather than a bunch at a time. So I will put that on the docket for tomorrow, and by tomorrow I mean Friday. All right. Let's go ahead and move on to 4.2. It's okay. 4.2 is about the mean value theorem. This whole section, or this little grouping of sections that we're going to do is very theorem heavy. So there are things in here that like, this is another one along with the extreme value theorem that's like got a proper name. You need to memorize this. Now we're going to start with something called Rolle's theorem. And Rolle's theorem is really just a tool on the way to prove the mean value theorem. So even though it has a name of its own, it typically doesn't come up a lot as a content-related idea. It's more kind of like background. But Rolle's theorem says let f be a function that satisfies the following 3 hypotheses. It's continuous on the closed interval a to b, differentiable on the open interval from a to b, and the endpoint or the endpoints of the interval evaluate to the same place, right? That f of a is equal to f of b. So the start of your interval and the end of your interval are the same height, right? What it says then is that then there's a number in that interval from a to b where the derivative has to be 0 at that number. So if we tried to draw it, it's like, okay, well, a and b the same height. I could draw it straight across, and then every x on that interval has the derivative 0. Everybody okay there? So I draw them the same height. Maybe I do like whoop. Well, there's a maximum. That derivative is going to be 0. Maybe I do one of these. Well, there I have 2 places where the derivative is 0. I do this. Well, there's still a place where the derivative is 0. And no matter how I try to draw this picture, I get a place where the derivative is 0. Mr. Kulik, the natural question is, why can't I do one of these where the derivative doesn't exist? Yeah, it violates the second hypothesis. So we're not allowing you to draw like an absolute value looking thing because the derivative would fail to exist there. Feel okay? Fairly simple idea, right? If we draw a picture and think about like what's happening, it's like, of course, if you have those 3 things going on, I have to get someplace where the slope of the function is 0. Everybody feel good? Okay. I don't want to prove this. I think that just kind of talking it through seems obvious why this needs to be true. I'm trying to get things, we're trying to accelerate things a little bit so I don't run out of time before the end of the semester. So I'm going to be honest. And I'm not going to prove this either. Can we do that? Let me think. How long does that take? Yeah, we can do this. Let's do this. That just takes a minute. I can't remember if we have something like this in our homework. All right. So the first thing that I would do is I want to show that I have at least one root, right? How would I do that? You could solve it. That's potentially a lot of work because that's a what? Well, it's a cubic.
Correct.
Well, assume you don't have a calculator, that I've walked over and just smashed your calculator with a sledgehammer, which is a funny picture. It's not quadratic. I'm disappointed. This is something we talked about in the first for the first test. It's a theorem we've used before. Intermediate value theorem. It is. Yeah. So clearly x cubed plus x minus 1 is continuous, right?
Yeah.
Why is it continuous? Because it's a polynomial. Very good. Excellent. Now all I want to do is find a value that makes f of x negative and another x that makes f of x positive. How about 0 and 1? Right? What is f of 0 going to be? Negative 1. What's f of 1 going to be? 1. Right? So since f is continuous and f of 0 is less than or equal to 0, just less than or equal to 1, there exists some c on the interval from 0 to 1 such that f of c equals 0. Everybody feel okay? So we've got 1, 0 here. Now the idea is we're going to assume that there is more than 1, and we're going to use Rolle's theorem to create a contradiction. Okay? So let's talk about this for 1 second before we dive into this. So proof by contradiction is a common technique for proving something. What you want to do is assume what you're trying to prove is false. And then if you can show, or assume that what you're trying to show, you want to assume what you're trying to prove is false, and then show that creates some contradiction. Like it violates some other thing that you've assumed. So what we want to assume is that this root being unique is false, i.e. that there's a second root, right? Really more than one, but without loss of generality, we can just assume there's a second one, okay? And I'll call it like C star or something. So we have some other root where we're equal to 0. So this is going to be like our A and B. And actually, let's add one other condition just to make life easier. Let's just assume that C star is bigger than B, or bigger than A. So that's like our A and a B in Rolle's theorem, right? So let's check. What do we have the conditions here? We have that is f continuous? Is f differentiable? Because what's the derivative of a polynomial? Another polynomial, right? So clearly that's defined, that's domain is all real numbers as well, so it's differentiable everywhere. We have f of c is equal to f of c star because they're both equal to 0. So we should be able to find some other number in between c and c star where the derivative is 0, right?
So for any polynomial that C star equals 0.
Just this polynomial. We're talking about this one specifically. And I'm going to use a K instead of a C. Okay. Now here's the catch. What's the derivative of that polynomial going to be? What can I say about the values that 3x squared plus 1 can take on? No, I'm talking about the y, the output. Yeah, it can only be, this has to be all positives, right? Or non-negatives. And I add 1 to it every time. So that value has to always be greater than or equal to 1. So can I, what have I just shown? That's my contradiction. Because somewhere in there, if there's a second 0, I have to have a place where the derivative is 0. And we just showed that it can't. That's our contradiction. That's a little tricky. And I skated through like writing out some of the steps because we just talked about why the conditions of Rolle's theorem were met. But that's the idea. Okay? Again, if you're going to take, 2, 3, 4 college math classes for your engineering degree, will not be the last time you see a proof by contradiction. Very, very common proof technique, especially for existence. Anytime you're trying to show something is unique or something has to exist or something can't exist, proof by contradiction is a really effective tool in doing that. Pierce.
Yeah, I'm confused. How does that help? So like you take the derivative. How do you get 1 on the right side?
So if I look at 3x squared, that always has to be greater than or equal to 0. And I'm adding 1 to it.
Oh.
So that derivative always has to be greater than or equal to 1.
Okay.
And because it has to be greater than or equal to 1, it can't be equal to 0, which is what would have to happen if I had a second root. You're welcome. Okay. This brings us to the mean value theorem. So the mean value theorem has 2 conditions. We need f to be continuous on the closed interval from a to b and differentiable on the open interval from a to b. If that's the case, somewhere on that open interval, there's a value where the slope of the function, the slope of the tangent line to the function at c is equal to the slope of the secant line for our function. So let's look at a picture and kind of visualize what this is saying. Okay? So let's take a look here. We've drawn a function. That's the black line from A to B. The blue line, that's our secant line. The pink is our tangent line. Do those have equal slopes? Yes, because the lines look parallel. That's the idea. Could this happen more than once? Yes, look at the second example here. Again, our function is the line in black. The blue is our secant line. And you notice there's 2 places where the slope of a tangent line would be parallel to that secant line. So we would say C1 and C2 are the 2 places where, the slope of our function is the same as the slope of the tangent line. Or sorry, secant line. Is that okay? What are the conditions I need? F continuous on the closed interval from A to B, and then F prime different, or F prime continuous, or F is differentiable on the open interval from A to B, right? So F differentiable on A to B is the same thing as saying F prime is continuous from A to B, right? Those are equivalent statements. Okay. All right. So let's look at the function x cubed minus x from the interval from A to B, where A is 0 and B is 2. So is that continuous from 0 to 2?
Yes.
Why? Great. Is it differentiable from 0 to 2?
Yes.
Why? The derivative is polynomial. Excellent. Okay, so we have the conditions for the mean value theorem, right? So we know there exists some C on the interval from 0 to 2 such that f prime of C is equal to f of 2 minus f of 0 over 2 minus 0. What's f of 2 going to be? 6. And f of 0? Can you find the value C now? Okay. So to do that, we're just going to take the derivative and set it equal to 3, right? Because we know that this derivative has to somewhere have a slope, has a value of 3. So how are we going to solve that? Algebra, very good. Yeah, so let's add 1 and divide by 3. And then we'll do the square root of both sides. Are those both our answers?
Yes. No.
No, why not? Has to be between 0 and 2. So we discard the negative. And we can say C then is just that. Does that feel okay? Not a big deal, right? The calculus was easy. The algebra is pretty straightforward, easy. Conceptually, you have to think about it, right? The hardest part about these set of sections is so much of this stuff sounds very similar. Like the extreme value theorem and the mean value theorem, like they share conditions that are similar. The names sound similar. There's the intermediate value theorem from before. They all sound similar. It's keeping it straight. But the actual mathematics, the number pushing or symbol pushing we're doing is pretty easy. Being able to select the right thing to do is the challenge, right? But the actual mechanics are pretty okay. Like nothing complicated, nothing, tremendously long and tedious. All right. So suppose that f of 0 is negative 3, and and the derivative of f is less than or equal to 5 for all values of x. How large could f of 2 possibly be? Go ahead. So I'm going to kind of just sketch a picture because, again, you read it and you're like, what? I think I even heard somebody say that. Okay. So what's the maximum slope that I can have from 0, 3 to x equals 1? 5. So I can go 1 over and 5 up, right? So that point could be 1, 2. That's the biggest possible or highest that point could possibly be, right? Because we're told the slope is at most 5. I'm sorry. No, the slope is less than or equal to 5,
Oh.
right? It's at most 5. It's the biggest it could be. So now going from 1 to 2, what's the biggest we could be? Could be 7, right? So f of 2 has to be less than or equal to 7. So we're just going 1 over 5 up, 1 over 5 up.
Oh,
Because the biggest change I can have, the biggest slope I can have is 5.
no, I got that, I just, I don't.
Well, it has to be
Seven
less
is
than-
not clicking.
You went from -3 to 2, and then from 2 to 7, so it's 5.
Why are we going to 7?
Because the next one, the slope.
Because we're interested in f of 2.
So why would we stop at 5? Why would we
It's just a slope. Right?
So I'm looking at the y coordinates because I'm looking at the maximum value for f of 2. That's the y coordinate. So starting at 0 to get to 1, I can go 1 over and 5 up. That's going to get from -3 changes to 5. To get to 2, I can go 1 over 5 up. That's going to change 1 to 2 and 5 to 7. And 2 to 7, right?
Oh, I got it.
Yeah, okay, good.
Sorry, that was like really, I don't know why.
It took a minute, that's okay.
Yeah.
It says, our next theorem that we have here says if f prime of x is equal to 0 for all x in an interval from a to b, then f is constant on a to b. What are we really saying here?
Slope is 0.
Yeah, so what is the shape of the graph on A to B? Yeah, just a horizontal line, right? I'm not going to prove it because it seems clear what's going on, right? Ideally, what would you do? I would use like Rolle's theorem and just show that like, you know, like, yeah, maybe not. Maybe that's a bad idea. Next one says if f prime of x equals g prime of x for all x in an interval from a to b, then f minus g is constant on a to b. That is that f of x is equal to g of x plus some c. So if two functions have identical slopes for every x, they are either the same function, right, or they're parallel. It's all is the same. So if the derivative is the same everywhere, the two functions are either the same function or they're parallel. So for example, let's say we have f of x is x squared and g of x is x squared plus 1. The derivative of f of x is 2x. The derivative of g of x is also 2x. Thank you, Rita. So there's a situation where the two derivatives are equal, but the functions are different, although they are parallel, right? They differ by just a constant. I have one last thing I included here. So how would we try to prove this? Yeah, I would use this idea here, I think. So what do we get if I do the if I say like f of x is equal to like tan inverse of x plus cotangent inverse of x? I'll do my derivative. Who remembers what the derivative of tan inverse is?
Oh, 1 over root 1 minus x. 1 plus x squared. Oh, 1 plus s squared. Oh, there's no square root of it?
Not in tan.
Oh, no, it was.
Yeah, and cotangent is the negative version of that. So what is the derivative here? So by theorem 5, we know that f must be constant, right? Which is exactly what it's saying here. Right? So if this is constant everywhere, we could find the value of c. So we know f of x is a constant, right? So to find that value of c, I can plug any number of x into this into f of x, and that should give me the constant, right? Now I have to be a little bit careful. No, I don't. The domain for tan inverse and cotan inverse are both all real numbers, so I guess I don't have to be careful about that. Maybe I do. I'm going to do 1, though. Why would I pick that? Unit circle, baby. Tan inverse of 1 is? Where is y over x equal to 1 on the unit circle? Pi over 4. Root 2 over 2, comma, root 2 over 2, which happens at pi over 4. Same thing for cotangent, right? Because that's just x over y. And we're done. Isabel. Of course.
So how can we plug in that can we plug in 1?
I could plug anything in,
Oh,
as long as it's defined.
so first you're checking to see if it's constant at that. The next thing.
As if it's constant, then f of x for any x should be just that constant.
Oh, so that second part where you plug in 1, do you not have to do that then? You already found in the stuff before that it's constant.
Well,
so
so that's getting the actual pi over 2,
oh,
right? That's how I'm getting it, that is actually pi over 2 and not, 7 or 19 or 26 or whatever. Like, how I know that the constant is pi over 2. So I've shown that f of x is a constant function using calculus. And then to show that that constant is pi over 2, all I need to do is plug any value,
I see.
which f of x is defined for, and that whatever that value is, I'm good, right? So here you have 1 through 11 odds, 15 to 17, and then 19 to 31 odds. A little bit shorter, yeah? Okay. I think next time we're going to do, my plan for Friday is to look at 4.3. I know it's only 40 minutes, so we may not do a 3-9 question on Friday. I want to point out to you guys, I also put in free response and multiple choice questions for this chapter. The multiple choice questions, for whatever reason, I started with the L'Hopital rule questions, which is the last section we're doing. I don't know why I did it that way. But you can just like bypass things that have any limit on them until you see things without limits. And then you can start, and you're going to see like mean value theorem ideas and extreme value theorem ideas, and go for a little while. And if you get to Friday, we'll have the first and second derivative test, and then you can do basically everything in here aside from like these first 15 or questions or whatever that are L'Hopital rule questions. Braden. So I put into my Notre Dame, let's see, let me grab it real quick. So I put in like the whole rest of the semester, my best guess at this point. So I have Friday of next week, or of the week we come back from Thanksgiving, as the open note test. So again, we're going to do 4-3 on Friday. That's my hope. And then do 4-4 on Monday, have a day to like clean up and review, and then try to do this open note test on Friday, the week following Thanksgiving.
Test. Did we all take it together as one big team with Mary? And then Notre Dame Maris.
No, but Mary can be like in your heart. Always. And if you listen, I heard that she knows a lot about calculus, so.
What?
Here's my fear for something like that. You guys talk about this being a good idea. My fear is time. Are you faster or slower with a second person?
My fear is you're gonna make it way harder because of partner tests.
I will guarantee you're going to move slower with somebody else than you would by yourself, because now you have to debate things and you have to have a conversation.
Would it be random partners?
But what if we run into the same situation we just did for the last one, and now you get to it's like, great, I did like half of the test really well, and the other half I didn't get to do because I ran out of time.
You both work out first, and instead of move on. It's not when you get there, like, I got 7, next question, come back.
Honestly, I think it would be good if you made a harder test with 2 people, because then it's like, if I do bad, at least I know one other person is going to do bad. You can blame the other person.
Wait, because it's open note, would you say you're making it harder?
Open homework.
But that's the thing.
Homework assignments. You can use your homework assignments.
So I can't print out all the MCQs and have them with me?
If they include your work on them, sure, that's a homework. Yes. Now you can't bring in like, she notes it has like the mean value theorem written down.
Oh, I can't.
You cannot. You can bring your homework that's been completed.
What if like my notes are in my notebook?
Oh, yeah, I got that issue.
That's why I told you before we started that like this is going to be open homework, and you have to make sure you're doing your homework in a way that it's now you can bring.
And we can't just.
So you can tear the homework out of your notebook, but it should be homework alone and no notes attached to it.
Like the example problems, you don't have one note, can I copy those into my notebook though? Because they're like.
If it's a homework problem that I assigned that we
But
did,
it could be like an example.
but it should not be an example problem.
What was the multiple choice?
You can complete the multiple choice and use those, sure.
But we have to write them down. We can't print out them.
No, you could print it,
Like, it can be so
You can't just like print his.
but you should, yes, it should be your work on it, not my work.
Yeah.
Yes.
Wait, what if you, like, instead of ripping out my notes, can I just, like, make a scan of it and print it?
Yes.
Okay.
Are you gonna make this test harder since it's homework?
It may be, instead of seeing, like on the previous test, you've seen things that were an exact copy of things I gave you in the multiple choice practice or even homework problems that I gave you. That wouldn't happen in this case, but you'll still see things that are pretty similar. That are like, okay, this question would be the same idea, but like they're decidedly different. Braden. I would expect to see, I'm still in the process of like writing your test. Right now, my plan was to do like 5 multiple choice in each part. So 5 with a calculator, 5 without. And then like 2 or 3 questions after in each section. Of those, I would expect to see, a 3.9 question as a multiple choice somewhere and as a free response somewhere.
So how many total questions?
I would say like probably 16 at max, including multiple choices, is kind of where I'm trying to end up. Again, I'm just getting in the process of trying to map something out. But part of it is like, find the extrema for this without a calculator. That's a time-consuming problem. Like, you have to do a derivative. You have to solve the derivative equal to 0. You have to plug in test values. There's some time, and then you run into like a 3.9 problem. Like, you have to draw a picture. You have to think about it. You might have to like eliminate a variable. Those take time. I'm trying to be, after what happened last time, I'm trying to be more conscious about what I'm asking you to do and the amount of time that you have. But that's kind of where I'm landing, is like 16 questions total. Now, some of those might have like some parts to them. Like you see like the big free response question I've had in each section. I'd probably still, one of the free response questions would be something like that. It has like some parts to it where I ask you to do a couple of things.
So like 5 FRQ without like calculator and FRQ without a calculator, and then 5 Q with the calculator.
So there'd be 2 sections with calculator without. Each section be the same stuff in it. So like 5 multiple choice, and then like 2 or 3 questions.
And no FRQ?
Like one of those questions may be FRQs, right?
Okay.
Like might be a multiple part FRQ. I haven't written anything yet, so I don't want to guarantee you anything. But that's kind of the format that I'm looking at.
Okay, so like 2 max FRQs though.
Yes,
Okay.
yes, yeah. And again, the stuff that I'm going to ask, like you to do with a calculator might be stuff that like you really have to have the calculator to do. Like this, if you have to solve a derivative equal to 0, it might be something that you can't solve by hand. So I can include some stuff like that just like you have to kind of have a calculator to do this. But that's what I'm thinking at this point. Is that okay?
Yes.
Again, like I'm going to do my level best to give you something that should be manageable and completable inside of 80 minutes. I think I got carried away on the last one because there's so many fun problems that I was like, oh, look at this. This won't take that long because I built like this trap door into the problem where you could have taken could have been a 30-second problem, and I get just like, oh, but if you don't see the trap door, then this is like a huge time suck.
If I do see chat, I don't trust it. I never trust it. I'm gonna
Oh, what? That was great.